You look like you're going to be more focused later. Go check. Be fast. You're going to have to run. Okay. All right. Run! All right. So homework is in the middle of the table. Paper picker upper. If you could go do your thing. All right. Aaron, you doing okay?
I'm doing. Yes.
Yeah. Celeste, you can just put that in the middle of the table as well. And all right, let's do a little bit of practice with this. If you guys can all stand up. Oh, we're already on. Am I looking good? Already getting a little juicy. It's okay. It's okay. All right. So just a quick recap of all the function adjectives that we know right now. In order for a function to be continuous, what has to be true? For a function to be continuous. Oh, no. For the function, the whole function to be continuous. Let's turn that up. For a function to be continuous, there can be no holes, no jumps. This is a jump discontinuity. No breaks, and no vertical asymptotes. Looking better, less robot-y. Good. All right, so that's in order for a function to be continuous everywhere. In order to show me that a function is continuous at a point, I think this is what some of you guys were preloaded for, right? In order for a function to be continuous at a point, what are the three things? The first thing to start with? Show. Did you get them?
Yeah.
You feel better?
Yeah.
Excellent. Get in here. All right, who cares where they are? He's got them. All right, so if the function is continuous at a point, first of all, show me that the function is defined at the point. This is one of the pieces we were missing on the unit test. You have to show that part. Next thing. Limit from the left must be equal to the limit from the right. Good, but remember with a limit, you're not talking about what happens when you get there. You could still have a hole. So the last thing, those limits have to be equal to how the function is defined. And this is where you want to be careful because I went too fast one time, poked myself in the eye. It was bad. All right, continuity, we got this? Good, differentiability. When I say differentiability, what does it mean? Not how do you see it on a graph, what does it mean? Differentiable just means...
The derivative.
One more time?
The derivative exists.
The derivative exists, that's all. The derivative can be found, it'll be a number, derivative exists. Now, next thing, you have a graph in front of you. You have a graph in front of you. What are the things you look for to see if the graph is differentiable? Let's get some hands on this. If you had a graph in front of you, what would you look for? Lewis, one thing you'd look for.
If the function is continuous.
If the function is continuous, because if it's not continuous, it can't be differentiable. Other things that you would look for. Cusp point, right? If you have a cusp point, is the function differentiable there?
No.
No, and the function that I want you to think about all the time, cusp point, absolute value of x. That is not the only kind of cusp point. They don't have to be this sharp, but like that's a really good one to think about with cusp point. There's one more reason why you'd see on the graph, and I don't know that we've ever seen one. Vertical tangent line. So not vertical asymptote, vertical tangent line. So like the thing that we talked about yesterday was for a function to be differentiable, that means smooth. The function must be continuous. There can be no cusp points, and there can be no vertical tangent lines. Okay, one more time together. In order for a function to be differentiable, in order for a function to be differentiable, no hand motions there, that is smooth. Smooth like I am smooth. Smooth like butter. Okay, the function must first be continuous. There can be no cusp points. There can be no vertical tangent lines. This is what you would see. Everybody good? If you wanted to prove it, you're going to have to go through all the steps for continuity. You're going to show like function is defined, limits exist, and the limits are equal to how the function's defined. You're going to look at the derivative, limit from the left. You're going to look at the derivative, limit from the right. If those two things are equal to each other, your conclusion?
It is. The function is.
Sorry, it is. I don't even know what that means. The function is differentiable at that point. Everybody good? All right, have a seat. Excellent. So now it's time to upgrade the skills. David, in honor of the fact that you've lost your keys but then found them, I need you to be the driver today. You're going to drive the laptop. Okay. Hey, this he turned in this reflection document yesterday. Yep. What? All right. David, you can come to my house. I'll take care of you. Oh, okay. I'll be fine.
That was it.
And by that, I mean like you can help with the laundry and the dishes.
Exactly, that's why I'm fine. I'll have to do that at home.
Check Caroline's homework. All right.
I'm good.
All right, time to upgrade the skills yet again. I know we are going at light speed. If we were in AB, we'd be here for like a couple of days. I want you to find...
17.
17, sorry. I was getting aggressive with the flipping. All right. So take a minute, read the information at the top of page 17 while Giselle calms down after her out. I'm going to keep exposing you all to these 3 different ways to find the derivative. I want you to see it again and again and again. Totally messed with. Yes, there's this new thing called the antiderivative. All right, so in the last unit, you guys kept finding derivatives like at a point, right? And if for example, the derivative was negative at a point, that always told you something about the original function?
Decreasing.
The function was decreasing at that point. If the derivative happened to be positive, your conclusion? The function is increasing at that point. If the derivative came out to be 0. No. Oh, there's not nearly enough people thinking here. If the derivative was negative, you guys would all tell me the function is decreasing at that point. If the derivative was positive, the function is increasing at that point. But what if the derivative is 0? Steve? Steven? Or was that Andrew? Sorry.
It's not differentiable.
Not quite. If the derivative is equal to 0, can you guys imagine? Derivative is equal to 0. That means tangent line has a slope of 0. Look at this graph over there. Are there any places where the derivative would have a slope of 0?
Maybe right there. Maybe right
Where, Aaron, where are you pointing to? Over here at x equals 1? Maybe. Maybe. There's a place for sure. At x equals 0 for sure. If your derivative is equal to 0, the conclusion here is you have a horizontal tangent line. It doesn't mean maximum, it doesn't mean minimum, it means a horizontal tangent line. There are more connections that David's going to expose us to. David, you ready to expose us? I need you to use your smarticle particles here. So click on show xp tan sec. Okay, what you're seeing here for this particular x value, we have point P. Point P is on the curve. I've drawn a little black tangent line. You guys know that this is called a, never mind, I just used the word, it's a tangent line. It's tough, I only get to do this once a day now. P is your point of tangency. The black line is your tangent line. Okay, and if you totally want to cheat, hey, all those values are over here. Newton couldn't do this. He didn't have the benefits of geometry sketchpad or electricity. All right, so David, slide x. Slide x. And so as x moves, your point of tangency moves, and it keeps redrawing the tangent line. Everybody okay? All right, I want to introduce you to a new idea. David, click show xf prime.
Whoa.
No, just once. Click, David.
One.
Okay. There you go.
Oh.
So f prime is this other point. Let me tell you a little bit about this f prime green point. It's hard to see that it's green. Maybe we want to turn off one of the lights in the back. As x moves along the x-axis, oh, that's better. Obviously, point P is moving. Your tangent line is changing. The green point, David, when it comes back on the screen, hit pause.
What?
I mean the slide button.
What?
Hit pause.
Hit it.
Okay, let it go for a little bit. There we go. All right. This green point is always going to have the same x-coordinate as point P, the point of tangency. We okay?
Yeah.
The y-coordinate is determined by looking at the slope of the tangent line. So this green point always matches the x-coordinate here, but the y-coordinate is going to be determined by the slope of this tangent line over here. Okay, let it go. Okay, there's the green point. Everybody good? I want to show you what would happen if we traced out that point. There's things that your smarticle particles should be doing as you're looking at connections here. Okay, David, show f prime. I want to show you guys this other graph. This other graph, f prime, is if you were tracing f prime's path as it goes across, here's the green graph and there's the blue graph. Have a quick conversation. What patterns are you seeing? What connections are you making?
Yeah. Yeah.
What connections are we making? Talk about this with your neighbor. David, what connections are you making? I'll be your neighbor.
The point is
Can we actually borrow?
Okay.
Yes, because the slope,
Actually borrow
And how do you know that?
the slope of the tangent line is P, when P.
Love, 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 love. All right, there is a place here at the bottom for you to start making some connections here. David, what was the thing that you just shared with me? What did you notice?
I said that I see two horizontal tangent lines.
You know you have two horizontal tangent lines. How do you know that?
Because if we look at f prime,
F prime, the green graph. What happens with F
If
prime?
intersects x equals 0 twice.
At x equals, okay, I want to be careful. X equals 0 is an x coordinate. I think you mean it intersects the x-axis.
Yes.
It intersects the x-axis at 0 and at 1. Great connection. So when the original graph, so if you're writing this down, when f has a horizontal tangent line, what do we know for sure about f prime? F prime equals 0. There's another fancy word for that. F prime has a, not a horizontal tangent line. F prime has a root, right? F prime is equal to 0. Other connections that we're noticing. Connections between the blue graph and the green graph. What else are we seeing here? When the blue graph has a horizontal tangent line, the green graph is going to have a root, was one of the connections. Lewis.
We said that the green graph, the f prime is basically the slope of f of x.
Right, the green graph is telling you the slope of the blue graph. So how about on this interval where the blue graph is, what's the word you want to use here? The blue graph is decreasing. What's happening with the green graph? Everyone always makes that connection first. It is true that the blue graph is decreasing and here the green graph is increasing, but look what happens. Now the blue graph starts to increase and the green graph is still increasing, so that's not necessarily a connection that's going to work all the time. I'm looking for something you can say here where the blue graph is decreasing that is true about the green graph. Carmen, what are you saying?
When it's the blue graph is
When the blue graph, the function is decreasing, the green graph,
negative.
the green graph is negative. Remember, what's the green graph? It's the slope. It's the slope. So if I'm decreasing, if the blue graph is decreasing, the green graph should be negative. Does the flip of that work? Right? When the blue graph is increasing, the green graph is positive. And this is the connection you want to be careful with. Blue graph increases, green graph positive. So what you want to capture here, function increasing, derivative is positive. Original function decreasing, the derivative is negative. And when you have the original function as a horizontal tangent line, the green graph is it's going to have a root. Okay? Now we are not at a point yet where I can tell you exactly how high up the green graph goes or how far down the green graph goes. But what you should know for sure are roots, and you should know like positive or negative when you look at like increasing and decreasing. So let's see how good you guys are at this. On the next page, there is another graph here. The partner practice at the bottom of page 18. I want you to give me a quick sketch of what you believe that graph looks like. I would encourage you to only use pencil. Only use pencil here. You really are only going to want to use pencil here. David, let's stop sliding X. And let's go over to model 2, the cubed root. And don't do anything yet. What you've got in front of you is the graph of the original function. I'm curious to see what you believe the graph of the derivative is going to look like. Pencil only here.
Yes.
Andrew, do you even own a pencil? Remember the connections we've already established. When the original graph is increasing, the derivative has to be positive.
No, because
When the original graph has a horizontal tangent line, the derivative graph is going to be equal to 0.
Oh, this looks like
All right, David, let's see how good we are here. We've already got P. Let's slide X. Okay. Let's show XF prime. This is going to be that green point again. And show F prime, David. Okay. From walking around, just about everybody has that F prime had to be positive the whole time.
Yes.
I'm not seeing a lot of folks who are getting the behavior here correct. Think about the tangent line. Think about that tangent line as we're coming in here. And David, I want you to slow it down. Slow it down. By slow it down, I mean stop sliding X. Let me use the right words. Okay, stop. What happens with the tangent line? As you get closer, what's happening to the graph? It's getting steeper and steeper and steeper. And if you could do this, David, I don't know you're going to be able to do this. Slide X, then you're going to hit the button again real quick. Not fast enough. Nice. Get as close as you can to X equals 0. You're not good at that. Okay. What's happening at X equals 0? Your tangent line is going vertical. This is a vertical tangent line. What happens with the graph of the derivative? What you're going to have is you're going to have a vertical asymptote. I want to be careful with the connection here.
No.
If your original function has a vertical tangent line, we know that's one of the criteria to look for differentiability. If you have a vertical tangent line, what happens is the derivative doesn't exist here. It doesn't exist in a very special way. It doesn't exist with a vertical asymptote. Okay? All right, David, we're going to go back to the original function, and I want to show you guys one more thing.
Model 1.
Go back to the model 1. And David, we're going to show xf double prime. And we're going to hit slide x. It moves way fast. David, the next time you think you can catch it, stop sliding x.
Oh, there we go.
F double prime. Or as somebody liked to say the other day, F prime prime?
Who said that?
I don't know. F prime prime.
That was idea.
Which is F, properly said as F double prime. It means the derivative of the derivative. Okay, let's let F prime prime go again. So hit slide X. Okay, let's start having some conversation what connections you might be seeing here. It goes way fast.
Wait, can you have him stop it?
Yeah, you can have him stop it too.
Oh, and also the slope of the slope.
All right, David.
Oh,
He's not very good at
Stop when he
listening.
gets the exit for one.
what?
It's basically the slope of the slope.
All right, David, we're gonna. Did you actually get it?
Yeah, it's right there.
Like,
Dang!
Look,
Super close.
X
Like way close.
is
Okay.
1.00.
All right, Aaron, why did you want to stop at x equals 1?
Because I wanted to see how F double prime aligns when it has when F prime hits its root.
Okay. And what are you noticing there?
That same kind of the same thing, but the Y value is completely different. I think it's trying to notice how it interacts with the.
We're looking at f prime prime, f double prime.
Mm-hmm.
Okay, David, show f double prime. Show the graph of f double prime. I think having the graph of f double prime might help make the connections a little stronger. Unfortunately, with the projector, you're not seeing the different colors. Right, so you've got the blue graph, which is the original function. You've got the green graph, which is f prime. And then you've got this other thing in here, which is f prime prime, f double prime. Okay? What are we seeing?
I'm
Yeah.
seeing that blue.
But Celeste, are you able to see it? Like it's like blue or pink?
Yeah, it's blue, pink, and green.
Blue, pink, and green over there. The f prime prime is the graph of the derivative of the derivative. So let's see if this works. When the green graph is increasing, what should this new graph be doing? Green graph is the derivative. If this guy is increasing, then the second derivative should be
Decreasing.
It's increasing.
if the green graph is the derivative, think about the slopes of tangent lines that you'd be drawing. Aren't they all positive? This graph over here is f prime prime, f double prime. When the green graph increases, this new purple graph should be positive. It's a connection between increasing and positive, or decreasing and negative. Right? So green graph increasing, purple graph that looks really blue right now is positive.
And when it starts decreasing,
Green graph starts to decrease, purple graph negative. Green graph starts to increase again, purple graph positive. What about up here when the green graph has a maximum? You've got a root. When the green graph has a minimum, another root. All the pieces start coming together. Okay? Now there's one more relationship, and I don't know if anyone's actually going to see this. David, hide f prime for me, and then we're going to summarize all the stuff. So hide f prime. I want to look at, yeah, blue number 1 and blue number 2. All right, let me try to emphasize this a little bit differently. The thing I'm going to highlight in green right now, and I think, Lewis, maybe we want to turn the lights back on. I don't know that that necessarily helps much. Okay, we've got the blue graph, which represents the function. So this guy here is like f of x, and the green graph is f prime prime, f double prime. There is something that we would use, and it's a word you maybe haven't used since back in the day in pre-calc. It has to do with concavity.
Oh god.
There's two kinds of concavity that you know about.
Concave up,
Concave up, like a cup that would hold
Yes,
water,
concave down.
and concave down, a cup that would not hold water.
With that cone.
Would everybody agree that this graph that I'm tracing in purple right now, the original graph is concave up?
Yes.
Yeah.
And what do we notice about the blue graph? I mean, the green. F double prime.
concave.
Purple is concave up, the green is,
Positive.
let's see, any other place where the green graph, where the original graph is concave up?
At 1-4.
From like right here? Concave up after that? Concave up? Concave up? Look at the second derivative graph. You're concave up all the way up until this point over here, and then after point P on forever.
Yeah.
What's happening is that if F is concave up, let's see if we can get this right. If F is concave up, then F prime prime is positive. You're above the x-axis, and unfortunately the colors are not working so well for us right now. F is concave up. Green graph is positive again. Okay, and I know you guys are good like pattern matchers here. If F is concave down,
Double prime is there.
then F double prime should be negative. Let's see, is that actually true? It looks like I'm concave down in this interval over here. Is F double prime negative? I can see it's below the x-axis. It's not perfect, at least like Geometry Sketchpad and the projector are not doing great, but these relationships are true. The other thing you can say, we had some conclusions that we made about F when it's increasing and F prime. F is increasing, F prime has to be
Positive.
positive. If F is decreasing, then F prime has to be negative. If F has a horizontal tangent line, then F prime is equal to 0. And the last one said if F has a vertical tangent line, what's the thing that we know?
Then there's a vertical asymptote.
Then F prime doesn't exist. F prime has a vertical asymptote. So F prime has a vertical asymptote. So these are some of the relationships that we're going to start exploring over the course of the next couple of days. What I want you guys to do is just take a minute or two, make sure you've summarized these. David, you've done a great job. If you want to return over here to work with the friends, that would be good. Make sure that you're comfortable with all these F prime relationships and the F double prime relationships. And then I want to push a little bit more. You guys are gonna love it.
Yay.
Thanks, David. I appreciate the sympathy. Sorry. The enthusiasm. Make sure you've got all those relationships down.
Vertical tangent line. No, F prime.
F has a vertical tangent line.
And F
Prime.
The answer is always yes.
Oh, did it?
Oh my God, you guys are gonna love this next part.
I wonder if the graph of F prime. I wonder if the F prime graph, but I made the F prime. I made it look only for
One time I tried to take these out for the work part.
Oh, don't get a lot.
Okay.
Like, my foot was on the break.
All the friends are good? All right, without looking, let's see how good we are with this.
Yay.
Cover up your notes. Cover up the notes, cover up the notes, cover up the notes. All right, do not call it out. Somebody put a gag on Celeste. I know this is going to be hard. All right. F is increasing. What do you know for sure? What do you know for sure? David, what do you know for sure?
F prime is positive.
F prime is positive. Love it. F prime is equal to 0. What do you know for sure? F prime is equal to 0. Steven.
F has a horizontal tangent line.
What about horizontal tangent line? F has a horizontal tangent line. F has a vertical tangent line. Can you guys show me vertical tangent line? Vertical tangent line. F prime has a, Aaron. Vertical asymptote. Nice. F is concave up. Can you guys show me concave up? Draw concave up. What? Dude, what are you doing? No, what did you like? Shooting gang signs over there. Concave up, a cup that would hold water. The thing that you know for sure. What do we know about concave up? Concave up. If you don't raise your hand, I'm going to start throwing lifesavers at you. Giselle, what do you know? F is concave up. What do you know for sure? Okay. Myra, help her out. F double prime is greater than 0. Okay, Giselle, F is concave up. What do you know about F double prime? Hold on, no, we were still on the same question. F is concave up. F double prime is greater than 0. F double prime is, wow, you're quiet and can't catch. F double prime is negative. The thing that you know for sure, I lay. F double prime is negative. F is?
Concave down.
Concave down. Nice. Everybody good? All right, I think I forgot to give one out back there. Maybe I forgot to give a couple out over here. Maybe I forgot to give a couple out over there. Share them, please. One for the friends at North Central. All right. And Mr. Link was having a rough morning. He wants some lifesavers too. All right, we've got 14 minutes. All right, shut up. If any school leader is seeing this, I did not just say shut up. It was somebody that walked in that sounds like me. All right, here we go. So now it's time to upgrade the skills a little bit more. I'm going to take away the graph. Yeah, I can do that. I have a master's degree. All right, part A, on what interval will the graph of f equals 3x to the 4th minus 8x cubed plus 6x squared be increasing?
You gotta prove continuity.
Come again?
F of x equals 3x to the 4th, what is it, minus x cubed plus 6x squared. The question is, where is f increasing? Does anybody know what this graph looks like? With certainty, no. Like, you wouldn't be able to go point by point, but I think you know some things, thanks to Mr. Link. You might look at, like, the degree, right? The degree, I notice that the degree here is 4. That means even degree, not even function, even degree, that told you something about end behavior. Right, it was either doing this or doing that.
Yep.
Which one?
Probably this.
It's gotta be up. Why?
It's the coefficient of the highest degree.
You look at degree 4, because it's even, their tails are both up or tails are both down. The way that you decide for sure though, Aaron, you look at the leading coefficient. Leading coefficient is positive, they both go up. Everybody okay? Now here's the thing though, more than that without a calculator is going to be really hard unless you have some, David, you okay?
Yeah.
Unless you have some calculus skills, this is going to be awkward. Here's the nice thing. When I say f is increasing, you all know already this means something about f prime. F prime is
Positive.
positive. Great. Hey, guess what? You know how to find f prime. Everybody knows what f prime is. F prime. Take like 5 seconds. It'll give you f prime.
to the power of 3
12x to the third.
Minus 24x squared.
Minus 24x squared.
Plus
Plus 12x. Great. That's true. Now all I need you to do is figure out where that guy's greater than 0.
That's
If I
perfect.
what?
Okay.
Make it
That is
equal.
equal to 0.
And what you would do back in the day is you wouldn't actually start here. You'd say, well, let me start with the question, where is 12x cubed minus 24x squared plus 12x equal to 0?
Or you find roots.
And then you're going to find the roots. I need clever stuff here.
Take out your bed.
Take a 12.
These are convenient numbers. These are not accidental numbers. Okay? They are all factorable by 12. Even better. X. What am I left with? X squared minus 2x plus 1. Hey, how convenient. I can factor that too. Okay, x squared minus 2x plus 1. What is that? X minus 1 and x minus 1?
Yeah.
All right, where are my roots?
X equals 1.
X equals 0.
X equals 0.
And it's equal to 1.
X equals 1. And x equals 1. Right, fancy word here. You call this a double root.
Oh, it is.
Which means it's a kiss, right? It kisses the x-axis. Don't kiss it, okay? Kiss it. Leave it alone. Okay. Here's what we're gonna do though. This is the new piece. It's called the number line test. We're gonna make a number line for f prime. I'm gonna call this my number line test. On my number line, I'm going to put the important things I know about f prime. I know that at x equals 0, f prime is 0. I know that at x equals 1, f prime is equal to 0. What I want though is I want to know where f prime is positive. This is what I really want. Where's f prime positive?
Oh.
Yeah.
From negative infinity to 0, and then from 0 to 0 to 1, and then 1 to.
Enjoy your lifesaver. Okay. Everybody, okay, we're doing a number line for f prime. I know what you're doing. And it's good, and I want to come back to what you're thinking about. What I'm interested in is where is f prime positive? Because really what I want to know is where is f increasing? I'm making a number line for f prime. I need to know where f prime is positive. Here's the strategy. We know f prime is equal to 0 here. We know f prime is equal to 0 here. Could it be equal to 0 anywhere else? Could there be any other roots?
No.
Not that you know of, and this is a continuous function. IVT starts coming in here. I have a root here and a root here, but nowhere else. So what I want to know is, what about in between? In between, could the graph be positive and be negative?
Only one.
In between, could the graph be positive and negative at the same time?
Yes.
Oh yes, it can go.
Wait.
You can't prove that though.
It can go like this.
Wait, yeah.
Let's back up on the logic here. You have a root at 0. You have a root at 1. Algebraically, there are no other roots. My question to you was,
it can only be one.
could the graph be positive and negative?
No, you don't have any more roots.
It's one or the other. You are above
Or
or you're below. If you were both, what would happen?
You have another
You need
root.
another root.
I get another root. I can't have another root. I'm above the whole time or below the whole time. So what we do, we do a test value. So pick a value between 0 and 1. So I'm going to take my test values over here. Give me a good value between 0 and 1. Half. Okay. Here's the thing. At x equals half, I want to know about f prime. F prime is this guy over here, which we factored down to this guy here. So what I'm going to do. At x equals a half, let's test f prime. So I'm testing right here. 12 times a half? 6. A half minus 1? Negative a half. A half minus 1? Still negative a half. Now before you're tempted to say, oh, 6 times negative a half times negative a half, I know what that is. There's only one thing I care about here. Is this a positive or a negative?
Positive.
This is a positive number, what I'm going to do over here is I'm going to say that means that my derivative must be positive, not just at my test value, but at all values in between 0 and 1. Okay? Now, after 1, what's happening? I'm either above or I'm below. Before I get to 0, I'm either above or below. And Celeste, we're going to come back to your thoughts. Because I think I know what's happening. Test in each of these intervals and see what happens. So pick a good test value, like maybe like -1. Another good test value, maybe like 2. And tell me about f prime. Let's see, -1. What do I have? I have negative, -1 minus 1, negative, -1 minus 1, negative, negative times negative times negative, negative. If I test 2, 12 times 2, I just care about positive. 2 minus 1, positive. 2 minus 1, positive. So I'm getting a positive. So I am negative before 0, positive after 1. The number line is not your final answer. The number line is part of how you get to the answer. Right? The question was, when is f increasing? F is increasing when, what do we know about f prime? When f prime is positive, using the number line, when is f prime positive?
X equals 0 to...
From 0 to 1. I'm a big fan of interval notation, and I want to use it right here. At 0 is f prime positive. Look at your number line test. Is f prime positive?
It is negative.
It's not positive, it's not negative, it's 0. Don't include the 0. What about at 1?
Bracket.
No.
Wait.
Look at your number line.
Oh, no. Parentheses.
Also parentheses. Anywhere else?
1 to infinity.
And then from 1 to infinity. The number line cannot be where you stop the conversation. F is increasing because f prime is positive. The number line helped me get to the information. Everybody okay? You guys ready for a push?
For real.
Try part B.
What?
Try part B. Yeah. Yeah, you get it. Keep talking group. Myra and all the friends, I think I forgot to mention this earlier. The assignment for tonight is, it's in the problem set packet. It says assignment for number 24.
Yeah.
Yeah. Good answer, David. David, I told you how much, like, you're my favorite. I wonder why I haven't said that then.
It's on camera.
No, I asked him if I had ever said it. Very different.
You're not saying that.
Exactly. F concave up.
The point of it is
If F is concave up, what do you know for sure? F is concave up. What do we know for sure?
Wait, what?
Don't worry about it. If F is concave up, what's that? Oh, can you leave it okay? Right, the relationship that we know, F is concave up, the thing that you know, is about F double prime. Eileen, what do we know for sure about F double prime? Oh, I'm sorry, one more time?
F double prime.
F double prime is positive. So good news, I can find F prime pretty quickly. Minus 24x squared plus 12x. But don't stop there, because what you really need is F double prime. And 36x squared minus 48x plus 12. I want to know where that's positive, and we've only got like 2 minutes, so I'm gonna go fast, but is everybody mostly okay with where we're going?
yes.
Okay. What I really care about is this connection between concave up and second derivative being positive. That we know how to get to the second derivative. And now this is just going to be like number line practice stuff. 36x squared minus 48x plus 12. Hey, convenient. Factor out of 12. 3x squared minus 4x plus 1. Let's see, I think, bless, that factors as 3x minus 1 times x minus 1. I want to figure out where this is equal to 0. I think you guys can tell me exactly where that's equal to 0. Alright, I need 3x minus 1 equal to 0. Is that a third?
Yes.
X minus 1 is equal to 0. That means 1. I'm going to go over here. I'm going to build my number line. Here's f double prime. X equals a third. X equals 1. I've got a root and I've got a root. Okay, just real quick. What's this the graph of?
Prime.
Prime. But it double prime. Yep. This is a parabola. Opening which way?
So it's
Up. If you know the roots, what has to be true?
Oh, from x equals 1/3 to x equals 1, the...
Think about your parabola. It does this, right?
Right.
So it must be negative and positive outside there, which you could also get by testing, right? You could test your conclusion then. F is, what do we say? F is concave up implies F double prime is positive. So we're going to say that's from negative infinity to a third and from 1 to infinity. Nice job. Nice job. We're going to pick up with this tomorrow, and yay, the camera made it all the way through the lesson today.